And so everything we do is available on biomedical.com. Go check out the website, provide your feedback. We will turn it into prompts for future development.
Okay, so picture this. You draw basically any shape you can think of. Could be a circle, yeah. Or something way more complex, like, I don't know, a treble clef.
Or even Homer Simpson, apparently.
Right, even Homer Simpson. And then you just watch as it gets perfectly redrawn, almost like magic, just by these simple spinning circles. So today, that's what we're diving into, Fourier Series visualization.
Exactly. And our mission, really, for this deep dive is to kind of get our heads around the core idea behind this, well, this really cool interactive tool.
Okay.
It all goes back to Joseph Fourier, his big discovery that essentially any periodic signal, or in this case, like a closed 2D shape, you can represent it just as a sum of simple sine waves.
Simple waves making complex shapes.
Right. And the visualization, the tool we're looking at, it uses these things called epicycles, rotating vectors. It's actually a term from old astronomy, kind of repurposed here.
Epicycles, like circles on circles.
Pretty much, yeah. Little rotating vectors demonstrating this whole idea of simple cycles building up something complex.
So that's the core concept then, breaking stuff down into waves. How does this visualization actually, bring that to life? Because it feels really intuitive when you see it.
It really does.
I mean, you can literally draw whatever shape you want or pick from presets. You mentioned Homer, but also like a square, circle, heart.
Treble clef. Yeah.
And you can fiddle with the controls too, right? The number of vectors, how fast they spin.
Yep, exactly. And the how is where it gets really interesting. Each one of those spinning vectors you see, that's one piece, one term of the Fourier series, a building block.
Okay, one vector is one part of the recipe.
Precisely. And the length of that vector, that tells you the amplitude, how big that particular wave component is, the speed it rotates, that's the frequency.
Right. Amplitude and frequency,
and all the details, the exact size, speed, even the starting angle or phase, it's all packed into these mathematical things called Fourier coefficients, often written as CRAN. That's like the specific instruction for each circle.
So the math tells each circle exactly what to do.
You got it. Then you stick these vectors together, tip to tail, one after the other.
Tip to tail, correct.
The very end point, the tip of the very last vector. That's the point that traces out your original shape.
Wow.
It really is that aha moment, isn't it? Seeing this like intricate shape just emerge from simple circles spinning.
It really is. It feels like finding, I don't know, the hidden clockwork behind something beautiful makes you rethink what simple can do. But, okay, beyond the cool visuals, why should this matter to you listening? What's the bigger picture here?
Well, stepping back, this idea of breaking things down, decomposition, it's incredibly powerful, like really powerful.
Oh, so
it lets us take super complex information. Maybe it's an image, maybe it's a sound wave, maybe it's financial data, and just break it into simpler, manageable bits.
Right, understandable parts.
Exactly. And think about where that's used. You know how MP3s work? Compressing music, that's Fourier analysis. Or cleaning up noise from an MRI scan in a hospital, same principle. Analyzing vibrations in a bridge for safety. Again, breaking down complex vibrations into simpler frequencies. It's not just theory, it's fundamental.
So it helps find order in what looks like chaos.
That's a great way to put it. And, looking ahead, people could make these visualizations even faster, maybe using something called the Fast Fourier Transform, the FFT.
FFT sounds important.
Oh, it is. It's basically a super efficient algorithm to do all these calculations, like lightning fast, essential for real-time stuff with huge amounts of data.
Okay, that makes sense for performance. So if we can break down images and sounds, give me a really concrete, maybe surprising example where this breaking down is crucial.
Okay. How about speech recognition? When you talk to your phone or a smart speaker.
Yeah.
Your voice is a really complex sound wave, right? The system takes that wave, uses Fourier analysis to break it down into all its different frequencies, its basic components.
Ah, I see.
And then it analyzes those simpler frequency patterns to figure out the words you're saying. It has to deconstruct the complexity first.
So it hears the ingredients of my voice, not just the whole sound.
Pretty much. Which kind of leads to a thought, maybe for you listening. If a complicated drawing is just a sum of simple rotations, and a voice is a sum of simple frequencies, what else out there seems impossibly complex?
Like what?
Maybe patterns in the stock market, the weird world of quantum mechanics, maybe even, I don't know, biological rhythms. Could they also be understood by finding their simplest repeating parts? It really makes you question how we even look at complexity.
Yeah, that idea that complexity might just be layers of simplicity, that goes way beyond drawing shapes. It's a whole different lens to view the world through.
It is. And once you start looking for those fundamental pieces, those building blocks, everywhere, well, it can really shift how you see things that seemed messy or random before.
A new perspective unlocked by circles.
You could say that. Understanding the building blocks definitely unlocks a deeper kind of insight.
I'll see you next time. Bye.